performance measurement. So maybe first, who has ever measured more than 10 million packets per second with DPDK in the room? Just one? Oh, more than 10. One. More than 50? Most few. More than 100? Anyone? Okay, 100. More than 200? So, Ari, we'll see what will be your numbers.
Hello, 1, 2. Hey folks, my name is Haaren from Haaren. I'm working with Intel. The last couple of releases of DPDK and last couple of years, in fact, I've been looking at optimization, so making software go faster. So while the guys before were saying, how can we try and optimize the power usage, I'm just looking at going maximum speed, try and throw everything at it and make your software run more performantly. So really getting more work done on one core is kind of where I've been focusing. So in your schedules, it says that this is a half-hour slot. It's actually a lightning talk of 15 minutes. And then Keith is talking on a similar-ish topic. I'm looking very much from a programmer point of view. So my audience is mostly you guys, I hope, who are looking at performance of packet processing software. And Keith has a bit more of a platform-level scope. So I'm going to be talking about a lot of details of software optimization. I'm going to have some screenshots of PerfTop and some of the real optimization tools that we're using to identify hotspots in your software, figure out ways to optimize it, things like that. So when I think about optimization, there's essentially you're looking at some software, there's code there, you're analyzing it, you're trying to understand what's currently running well, what's not running so well, and somehow you need to try and interpret that, understand what the bottlenecks are, re-implement it, or write some different code that achieves the same purpose, but somehow goes faster. And I break this down into kind of 3 parts. One is collect some data, right? Let's understand what's happening today. That's required to understand what is the problem. I tend to be quite data-driven in that, so let's make measurements. Let's just record what is actually happening, and there's some fantastic tools to do exactly that. So step 1 is really record data. Step 2 then is let's try and get insight into what this data means. And the real difference here is not that we're pulling in more data, it's that we're reading and trying to understand the data that we have to gain insight from it. For those looking carefully at the slides, you'll see there's a little star up there, because this is the hard part, and this kind of requires experience. So if you look at this data for the first time, it's very hard to infer or to kind of understand or to gain knowledge from that data. And I have a slide coming up on that to kind of try and place where I think is a nice way to look at that problem. Then after you have that insight, you have something novel. You as the human, in your brain, you have an idea like, okay, I think this might be the problem of this section of code. So then what you do is you go and you prototype some other type of solution to that where you avoid that particular issue in the code itself. So those are the 3 things, right? We record some data, we get some insight, and then we go try and do a solution. So jumping straight into that, if we look at recording data, there's a tool called Linux Perf, or it's part of the Linux kernel, basically. It reads the performance PMUs, performance monitoring units. So previously, in the power talk just now, we talked about reading branch hits versus branch misses. We talked about reading some other PMUs or some other counters that the hardware supports. So Linux Perf actually reads those same counters, but it programs them to do different things. For example, it checks where are you spending your cycles. So we can understand at runtime, while your application is running, exactly where your CPU is spending cycles. So on the graph or the screenshot on the bottom left, we can see that there's some code running. You see the names of your functions, assuming you've built with debug symbols. And it tells you the percentage. So I think you can just about see over here on the bottom left, how many percent of our total runtime of this particular CPU core is being spent in what function. So in this case, I'm actually monitoring OVS. The exact code base doesn't really matter. This applies to all software. But you can see I'm running PerfTop, which is the command to get that particular point of view, with a -C, minus capital C flag of number 1. That's the particular core or L core ID that I wanted to monitor in this case. And that gives you a breakdown from the top to the bottom of how many percent you're spending of your time in what function. If you hit enter, you get to the other right-hand pane view here, which gives you the assembly instructions that are actually comprising that function. So what is your CPU really doing? And in that, we can see that we actually have 2 loops. So they're highlighted with the blue arrows on the right. And it's part of the Miniflow iteration code for those familiar with OVS. Again, the code base really doesn't matter. It's generic concepts of here's a loop where we're spending a significant amount of CPU cycles is really what I'm trying to say here. We don't really have context at this point. We just see that this code is taking time. We don't know why. But we have data. So step one of our process of trying to optimize this code is pretty much done. So I talked a little about the insight earlier, but really I kind of have 4 things that when I try to piece together, okay, what am I really doing when I'm trying to look at these screenshots of data, when I'm trying to interpret this data, what are we really doing? And I try to break it down into these 4 bullets. So the first one is you need a mental model of high-performance code. So you need a reference point. In order to be able to identify things that are bad, you need to know what's good. And typically that's just in having analyzed code. So this, from the little asterisks on the first slide, is you need some experience. You need some reference point to compare the current code with the other. That's probably the hardest part of optimizing or getting more experience in optimizing itself, is having that mental model, is building up a concept in your brain of this is good code, or this is assembly instructions that are running well, and these are like instructions that are not running well for whatever reason. So as an example of good performance code is actually DPDK, and a lot of the high performance coding concepts that I learned a lot from came from DPDK, came from certain optimizations or certain design patterns in DPDK that are actually very high performant design patterns. So step one is build this mental model. You need to start really thinking about it. Step two is reason about your code performance. So think about what's happening, not just in terms of like, oh, my data structure assigns this to over here, but how does that really work inside the CPU? Is it going to be a cache miss? Is that going to be a branch? Is it going to be a branch miss? Could we utilize some SIMD or some ISAT to handle this better, or to do a more performant implementation? So there's a whole bunch of things there that we can investigate. Even just starting with branches and cache and ignore everything else, that's a really good starting point. Understand if a branch is predictable or not, and understand if the data or the memory that you're accessing is likely to be in L1 or L2. And with those 2 things alone, you could probably optimize your code a lot, if those are issues that are today in your code base. So the third thing then is you've just kind of made a mental model and you've thought about it yourself. So you now have expectations of a certain piece of code. You can expect a certain piece of a certain assembly line or a certain instruction to be expensive because it might be a branch miss or it might access something that's far away in your cache. So now you go and you measure it and you adjust your mental model based on that. So you're continuously iterating and trying to improve this mental model of good code versus bad code. And that's really the part that this goes on forever, right? You're just continuously updating. Every time I open PerfTop, I'm looking at some code, I'm thinking, okay, I expected that to be worse or better, and then mentally I kind of adjust what I expect next time I open PerfTop. And that's really what kind of guides you and gets that mental model well tuned to how your CPU actually behaves. And that's what gives you the context and the experience to be able to optimize code much more efficiently and much quicker, and to get more results in less time. And then the last thing is really to prototype and measure. So build something, like pull out a little micro benchmark, build that little snippet of code, do a benchmark of your existing code, then analyze it with as you have on step 2 here, so reason about it, understand what the bottlenecks might be. Take that, rewrite it, validate that the code still performs the same function, or that the end result is the same, and benchmark it again. And from that, you can kind of pull out the real, like, little golden snippets, I suppose, of this code used to run like this, now it runs with these instructions, this is 3 times as fast as the other. And sure, it's only a small little piece of code, but if a small piece of code operates on every single packet in your system, then assuming line rate of 10 gig or so, you still have 14.8 million of those iterations that's now going 3 times as fast. And because it iterates on a per packet basis, it's actually going to give you a significant end-to-end performance delta. So that's kind of the general insight, and hopefully that's not like, hopefully it's of some interest to you to kind of try and get some insight into what I'm doing. So going back to my previous example where we had these 2 loops, the only change here is not the data. It's only in the context of the slide. It's the insight that I've now annotated that assembly instructions. I understand what the loop is doing, because as part of gaining this insight, I investigated the code. So on the top left there, that's the first step. We went and we looked at the code that generates this assembly. We investigate what that looks like. If there's some macros and things, it's sometimes helpful to just copy paste in the macros manually, because then you end up with, just straight line C code that you can easily read. As part of this, I realized that in certain use cases, so for those familiar with OVS, per subtable, there's a fixed loop trip count. So the amount of iterations in each one of those loops is actually fixed for a given workload. For example, if we have a VXLAN packet or a UDP packet, to parse the outer of that, it always iterates 4 times and once. Not a typo on my slide. This code is slightly different to the exact UDP use case. So we have a known loop trip count. That's really the insight that we got. So there was no change in the code. There was no change in my measurements. But as a programmer, I now understand for this workload, and if that's my common workload, that's the one that I want to optimize for. For that workload, I have a known loop trip count, and we can use that new insight to try and optimize for that particular use case. So let's jump straight into what the solution actually looks like. Today, or at least let's say last OVS release, so 2.11, the February release, the code looked something like what we have here. If you look at the 2 blue arrows, those are my graphical representation of the loops that we had in the previous perf top screenshot. Loop A is the top loop, the first one that iterates an unknown number of times before we started our optimization. Loop B also runs an unknown number of times because at compile time, the compiler doesn't know. So it generates this function on the right-hand side as marked as generic. And what that means is basically it emits code that will always work for whatever loop trip counts you give to the function. So we can see that the compiler emits the assembly instructions for a loop. It says for a loop int I equals 0, I is less than whatever trip count we have. But it doesn't know the trip count, so it just emits a loop. And similarly for B, we get another runtime loop in the code base itself. So the compiler doesn't know at compile time what those loop trip counts are, but we as a programmer from our insight understood, wait, there is actually a specific loop trip count, and we can tell the compiler that. So if we look at the slide now, what we can do is we can give the compiler that context of how many trip counts there are, and you'll see in the blue highlighted piece here at the bottom, I've called the function above, but I've hard-coded the constants for those loop trip counts. So I kind of hacked it together a bit, but int A, int B are essentially the loop trip counts. And by hard-coding them at the bottom, the compiler now has that context. It has that context because the function at the top is marked as always inline. So the code that will be emitted for that function is always going to be inlined into this call here marked with the blue. And as an end result, when the compiler is actually doing its optimizations, it's going to identify this loop is going to iterate 3 times because I have a hard-coded constant loop trip count of 3. And there's no point in iterating a loop 3 times. We just don't gain any benefit from it. So it emits flat code instead. And by flat code, I mean there's no loop. It just literally puts 3 copies down in the assembly. Similarly, for loop B, it understands, hey, this iterates once. There's no point in doing that either. Let's just take the loop out because it iterates once. So there's no point in putting in our I variable. There's no point in putting in the checks to see if we iterate. And what you end up with is a function. So on the bottom right, and we can see now the pink arrows is the compiler's work. It took that code, and it essentially put 3 copies of A and 1 copy of B into the assembly, into the binary instruction stream, and returns. So instead of having 2 loops and then a return statement, we now have a specialized version of that function, which operates on 3 and then 1 loop iterations. That's essentially, we helped the compiler to optimize because we gave it more context. And the insight was what gave us that context of, okay, this iterates a number of times, 3 times, and then once. After that, of course, we have to validate or verify that this optimization is actually valid. Did the compiler really do what we wanted it to do? So it's all well to expect the compiler to do this, but we really need to double check it. And again, that's just a case of launching perf-top, just like we did on the first slide, to record our data, and then to check what has it done. And in this case, you can see the font size is a lot smaller because there's more instructions. And there's more instructions because we've now unrolled that loop 3 times. So it's flat code, essentially, right? There's no more loops. So it starts executing at the start of this instruction snippet and executes it all down to the bottom, does that once per packet, and the correct behavior is maintained for that particular use case. So you might say, hey, does that really matter? Like, okay, we have some code here that's now flat code instead of loops, but do we really care? And the answer is yes. So some people in the audience actually helped me benchmark those patches in OVS and reported somewhere between 10 to 15% end-to-end phi-to-phi performance gains on a UDP packet switching. So to think that these kind of optimizations are irrelevant, or, oh, that's micro-benchmarking, it's not going to make any odds, or any real difference in terms of my performance, well, 10 to 15% is what we got on phi-to-phi switching. So admittedly, there's no guest interfacing and things going on here. You can argue it's too simple a test. I'd agree. But still, if you want to optimize code, this is methodology, or this approach to the problem seems to be quite valid. That's the end of my talk right here. I'd happily entertain some questions. Please come find me otherwise afterwards in the hall. So I'm always up for chatting about low-level software optimizations and things. Yeah, if there's any questions, then please raise your hand. And the organizers of the conference have kindly provided me with some sunglasses so I can actually see the audience. All right. Well, fantastic. Please come discuss things in the corridors if there's further questions. Apart from that, I'll hand over to Keith, who's going to talk about the data plane. Okay, there is one question.
So Harry, loop enrolling is relatively simple. So it's relatively easy to find easy to look for. Do you have more complex examples that you intend to publish?
Absolutely. I'm particularly interested as well in folks in the audience like, hey, look, I have a performance issue with this little piece of code. Can you help? Post to the DPDK mailing list, drop me an email. My email's listed here. So absolutely, I'd be interested to see what issues we have as a DPDK community and to try and work on that. But do we have more complex examples? Absolutely, yes. For example, once you understand that you can unroll that loop, you can also start considering doing SIMD versions of it. So we can use, for example, our single instruction multiple data to try and run those 4 iterations in parallel in one instruction stream. So there's a huge number of things that occur. By actually inlining this, the compiler can do a much better job at instruction scheduling. So previously it wasn't quite as aware as to how those instructions were interoperating with each other. But because it's now flatline code, the compiler sees the dependencies much more clearly, and it actually runs at a much higher IPC, so instructions per cycle. So these kind of optimizations, although it seems like, oh, you just unroll the loop, in reality, the things that you can gain afterwards and the differences in compiler output are actually huge. So that's a thing. Don't know, is there a question? I'll hand over anyway. Look, for the rest of the questions, you can find me after the talk. Thank you.
Okay, I'm Keith Wiles. I also work for Intel. So we're going to talk about a performance monitor tool that I've been dealing with or working with and trying to get completed. So, okay, which arrow is it? Okay, so we were playing with trying to figure out how to understand DPDK applications and how do you understand what its performance is, whether it has bottlenecks, is it bottlenecks in the system, is it bottlenecks in the application, where is these performance bottlenecks at? And this is where this tool is coming from, right? We have a lot of tools and a lot of stuff inside our Intel processors that you can dig out to find out intricate details about your code. But it's typically takes an expert to understand that stuff. So one of the things is I looked at this and I iterated over it, and it took me a couple of months to finally land on that. I'll go ahead and write it in Go. I'm not an expert in Go, been doing it for about 4 months. But I'm just an old C programmer. So one of the things I wanted to do is with this tool is to gather this information from the system, also from the DPDK applications, if we can find them and isolate that data. Then display it in a user-friendly way. We're not talking about developers using this tool per se, but we do want to allow developers to use this tool. But to be able to say that this information, this is what may be going on with your system. This may be a bottleneck. You need to go fix it, and this is how you may be able to fix it. So an analysis of that data is what we're looking for. And I chose Go because it seemed to be fairly reasonable for what I needed. It had a bunch of pieces that I could utilize and packages I could utilize. Somebody might say it's not the best tool on the planet, but it seems to work fairly well for what we're doing with this. This is not a DPDK application, by the way. This is just a standalone application. It uses VT100 cursor commands, fairly simple, and it uses ANSI color. So you can SSH into your headless machines and bring this tool up and look at it and see what's going on in your system. And that's what we're trying to do. So some of the areas we're trying to gather is the PMU tools, PCM tools, the registers, and the power-based frequency, which is Chris and David talked about, and also QPI, PCI, anything we can possibly stuff into this tool, we want to try to at least bring out so you can see it in one spot. Now, there's a lot of tools out there that do everything, but you have to go from tool to tool to tool, and they're all different formats. So we want to present this in an easy-to-use format. Right now, in this development phase, I'm just collecting the data and displaying it. So it's really not that user-friendly yet. So we want to get there. And this is where we can also look at, from the perspective of, I guess it was Martin that asked about, how do you know when your application's busy? Well, this is one way we can possibly pull that data out and at least show it to you easily, because we can pull a lot of different places, not just the application itself. So this is really kind of the big picture here. I guess this is the thing here. So this is just an X-term window. You can tell it's pretty simple. We'll see bigger pictures of this later. What we're trying to do is we're trying to pull information from these particular areas, right? All the hardware counters and everything else that are inside the CPUs, and also within the system itself. Then we also want to pull all the information from the DPDK applications to display back to you as well. Because today, if a DPDK application isn't built to display any information, it's a black box. And that's one of the complaints we hear. It says, oh, I have no idea what's in that thing. And if you do have anything coming out of it, it's typically done in various different formats. So let's try to display it in one place, or gather it in one place and display it and have people see it. We have this stuff over here, which is collect D and power management, or R&D. And right now the tool is just display and analyze type mentality. But I can see that we'll probably add some controls into some of the tool to allow you to change some things if you want. But we're not trying to be, the master of the universe and do everything that collect D does or everything that everybody else does. We're just focusing on performance of this tool, okay? And also be able to log this data in the background. Come on. Oh, there it is. So one of the other areas we're going to look at, and one of the reasons why I kind of went down the Prometheus path, the Golang path, is Prometheus is all written in Go. So it seems to be an interesting tool we could use. You could link it into this performance tool, or you could have it as a standalone tool. I'm kind of leaning towards a standalone tool, just the Prometheus client. Then we teach the Prometheus client back end to figure out how to get all this data from this tool and from the other DPDK applications in the system. Now, he does get some of that stuff from Collect D today. So we'll figure out what the balance is for that, right? So that you can record this over days and weeks and whatever, and you can actually see trends in your data. This tool isn't meant to run all the time. You could, but it's not meant to run all the time. The real kicker is to gather this data and then figure out how to analyze it and come up with possible solutions, or at least point out that, hey, you have all your cores accessing this NIC. This NIC happens to be on this NUMA zone, or on this PCI bus. This PCI bus is attached to this socket, which is a separate NUMA zone from where all your CPUs are located at. When doing packet gen, most of the time when people tell me, says, hey, packet gen is performing wrong, I tell them to send me what their CPU layout is, and they almost have never run CPU layout. They don't know where their cores exist on a dual system. And you'll find out that they were running, that their PCI bus on my machine at home is attached to socket 1, not socket 0. It's attached to socket 1. And I didn't realize that until I got digging into it. So I was allocating cores off of socket 0. Going across the QPI bus will really kick your performance. So that's what we're trying to come up with, is to point these obvious things out to people that we have learned, but it's not necessarily obvious to everybody else. So the tool, we want to make it a completely open source, BSD 3 clause supported. We want to make it a community-driven tool as well. Obviously, people who know Go can actually point out all the mistakes I've done in Go and make it better, hopefully. But hopefully we got a good framework here. We'll try to open it up and figure out how to get people to contribute to it and make it better. I can't do it all. Right now, there's a few counters we want to add to DPDK so that we can get some of this busy work or busy times, or whether or not you're running busy or not busy. I know some of it's in the application itself, but also DPDK doesn't give you any hints as well as to whether or not you're busy or not. Now we could add counters at the RX burst and the TX burst level. I've done that as an example. It didn't seem to affect performance in my level, but I'm only running 10 gigabit on my machine right now. So if you're doing 40, it might show some performance degradation, but in reality, people are willing to trade off a little bit of performance for at least insight into the application, and that's okay. And some people say, no, I can't give up performance. So we'll have to do a balance there, figure out how to add these counters without affecting performance if at all possible, or at least be able to turn them off when they don't want them. And that's another problem, but hopefully we can work to that. So it's all written in Go today. It's completely standalone application. It does require a few packages to be installed from the perspective of Go, but we are collecting all this information. There is a daemon that sits in the background right now from the PMU tools kit that you can get that's open source as well. It sits there and collects up all this information and stores it into a shared memory region. So that's where I'm collecting some of this information at. So okay, so I'm going to kind of jump into these some of the screens here. What we're looking at here is and these screens have changed, so if you went and looked at the code, it'd be different today. This one here is just listing all of the DPDK applications that I find today. And one of the ways I find the DPDK applications is I use DFS, or the DPDK file system that I wrote last year that I presented, that would give you a fused file system into DPDK. And today you can dynamically link that into, or LD preload it into a DPDK application at startup, or load it through the -D option. And it does, DPDK or the application doesn't need to know it's running. It uses constructors to start itself up. So it creates a file system, and I can collect the information and find the actual DPDK applications. Today, there isn't a way to necessarily find a DPDK application in your system. There's no indicator that says, hey, this must be a DPDK application, because they're all different names. Some of the remnants that we leave in the file system could be from old runs, could be from secondary processes that have gone away, or what have you. So we have to, that's indeterminate to me, and I don't want to go cruising through a couple of thousand process IDs trying to guess which ones are which. So this made it simple for me. If we can come up with a better way, I'd be more than willing to deal with it. So in this particular case, all we're doing is I'm dumping out what the command line is, which is another thing we don't see any evidence in DPDK. You can't tell what your command line is. This means you can't necessarily find out what cores that application is running on either. You can, but it's a tedious process. And then I'm dumping out some pieces here. Now, I'm colorblind, so don't get too excited about the colors. And I'm not a UI kind of guy, so I'm just an engineer, so I don't do very well with presenting data to people, so I'm hoping someone will help me with that as well. So this is just a view. If you select DPDK, it shows you some information about DPDK application that it knows about. If you select system, it tries to show you the system level information. This is the PMU counters that get dumped out. These are the individual counters that you can do. There's hundreds of combinations of these counters that you can deal with. And to tell you the truth, I don't know what all they are. So what I want to do is turn this into something we can actually use instead of this big eye chart of numbers. We don't want that. What we really want is something that shows you, hey, this one is too high or too low or some other number, right? Some other way to display this data in a more consumable way. These guys over here are just which of these counters do you want to display. So you select one of these, and it's just a JSON file. You just edit it, put it in there, and we'll collect up these files here. This one I did just for this IPC over here, right? The retired cycles per second, and the retired instructions kind of give you the number of instructions per cycle. So I'm getting short on time here. Here's a little graph indicator of what those are. What I like to do is get to a better one. If you select the core over here, you get the IPC out for that particular core, and you get to see it in a running thing. These graphs run continuously, and they scroll off the left side. So this one is really more of a top, I don't know, HTOP, whatever you want to call it. It just gives you information about your system. This little box over here, like I said, almost no one runs this thing whenever they finally confront me with packaging questions, right? And I say, tell me which cores you put it on and how you configured it, because chances are this is wrong or the command line's incorrect. And I'm sorry for the command line being so cryptic, but that's the way life is, I guess. And we show with these pieces here just basic system information. Nothing exceptional. What you'll see here is if, and I didn't capture that one, if you have a DPDK application here, you'll see this pegged at 100% for every core that DPDK is running on. And what we want to do is gather that information that Chris and everybody else is talking about and put it in red on top of that bar as to what the actual utilization of that core is for that application. And give you a hint that, hey, this thing is only really running at 10% or 1%, or hey, it's running at 90%. So, and we still have to, drill down as to exactly how you want to collect that particular piece of information. Okay, so here's the power save or the power-based frequency stuff that Chris and David did. So I just dumped out the registers here so you can actually look at it. And then with the CPU over here, you can graph which one or what's going on with the frequency for that particular process. So in here, this is dev bind, basically. I do want to add some control in here for dev bind to allow you to detach and attach application ports and so forth. The one thing that isn't shown in here is virtual devices, right? We probably ought to add virtual devices into here somehow so that you can actually do it. Since I have the command line, I can typically find out what the virtual devices are. Not always, because you can create them on the fly. So we'll print out all the devices. All these windows scroll, by the way. I didn't write this code. Somebody smarter than Go than me did it. Okay, so this one is just the PCI bus. And this one actually gives you a lot of information. Those values up there are extremely cryptic. And to tell you the truth, I don't know them all. Edwin over here knows them very well. So we'll come up with better verbiage and things to tell you what it really means, right? Because, the PCI read cur and all this and read for ownership and stuff like that, they mean things in certain values and how they're laid out. And we need to come up with a better way of displaying that and telling you exactly what's going on, that, hey, this is what's going on because you have a lot of these going on or something like that. So we'll get to there. Like I say, I'm just collecting the data today. This is all the QPI information, and there's a lot of it. And don't look at these numbers because I have the offsets incorrect, so I'm getting some really weird values. But this tells you a lot of information about your QPI bus, and that can give you a lot of indicator that, hey, you're crossing the QPI bus too much, or your thermal is too high for whatever reason, and stuff like that. So we'll get to that. And then we can graph whatever shows up in there, right? And we need to more dynamic. So that's basically it. That's the tool. I'm right at my 15 minutes or so. So we're really looking for a lot more help to develop this and produce it, and whether or not it's useful to people. So far, everybody says, yeah, I really want to see that tool and use it. But we really have to make it much more usable than it is today. So, any questions?
Yes, we have time for one question.
None today? Yeah.
These APIs you use to collect the information, how architecture specific are they?
Some of them are very architecture specific because of the PMU counters and stuff like that, right? But obviously, we can make this work on any platform. We just have to go collect that data and display it, right? It isn't so much that I can, like those little, I call them, people call them tabs at the bottom as to what the panel looks like is what I call it. But we can have as many panels as we want. We can even have sub-panels for various things, or pop-up windows, things like that.
We should integrate the architectural counters, right?
Yep.
Architecture PMUs, and we should, the I/O are typically non-architectural.
Correct, yeah.
But the ones that we had on the screen here were all architectural.
Yeah, yeah. I mean, it's the one we were really focusing on right at the moment, but I really want to pull those out and make it more global for everybody to use. Right? Okay, anything else pressing? All right, thank you, everybody.
Thank you very much. So the next talk